Okay, so today in class we worked on a problem with the wrapped around your finger effect, but some of you did not solve that problem. So this is an example to try to explain how that works. So what I've got drawn is a picture of the situation, and really there's three spots that you care about. One, which is what we're ultimately trying to find, is the initial height of this thing. Two, it's a spot a lot of you guys considered, and that's the spot where the mass is swung down at its lowest point. And three, it's a spot where if you got this wrong, you didn't pay attention to it, but that's really where the problem starts. And that is the fact that at this highest point, there is a speed, a minimum speed you have to have in order to successfully complete a loop-de-loop. Kind of like on a roller coaster. If you're not going in the right speed here, on a roller coaster, there are safety measures to make sure you can make that loop, but here there are not. So you have to have a certain speed to keep tension in the rope to make it go around in a circle. Okay. So what we're going to do first is start solving that spot. So at 3, we want to apply net force is equal to mass times acceleration. Okay, now at that spot, if I was drawing a picture of the mass at that point, there are two forces acting on it, potentially two forces. One would be tension, and one would be gravity, as this thing follows around in arc like that. So this is at that highest point in the loop back. All right, well, one of those two forces can get smaller, and that's tension. The slower I'm going, the less tension I need to redirect them. But gravity cannot get smaller. Well, what we were looking for is what's the minimum height we need to let go from to make this thing make the wrapped around your finger effect. Well, that means what's the minimum speed I can have here? If I'm looking for the minimum speed here, I want to make the redirecting force as small as possible because the redirecting force depends on speed. Okay, so the way I'm going to do that is the slower I go, the smaller tension gets. The smallest tension can become is 0, and at that point, gravity is going to give us all the redirecting force I need. Tension's there, but we're sending tension to 0. Tension is going to be basically nothing because I don't want to have any tension in the rope. I want gravity to provide all the redirecting I need. So then mg equals mv squared over r. The m's cancel, and rg equals b at that top squared. Okay. Well then, let me autofocus this. Let's get this thing to be autofocus. Yeah, it's a little bit better. Okay. That'll give us our speed at the top that we need, rg. All right, well now that speed is how fast I'm going at 3. Now I can use conservation of energy from 3 back to 1 because there are no non-conservative forces at play here. So let's do that. ME at 1 has to equal ME at 3. So at 1, I have all potential energy, M times G times whatever that height is. At 3, I have kinetic energy, 1/2 mv squared, where the v is that v top. And I also have potential energy, m times g, and this height I'm going to call 2r, because there's 1r, there's a second r, so that height is 2r's. Okay. So mgh equals 1/2 mv squared. I just solved for that v. That v is r, well, that v squared is rg. So 1/2 times mass times rg plus mg times 2r. Those masses cancel out in all the terms. The g's cancel out in all the terms. So it doesn't matter if you use 9.8 or 10 if you didn't plug in numbers to the end. And I get that h is 1/2 of r plus 2r's. So h, it looks like, is 5/2 of r. And that's what I'm calling my lowest point, 0. A lot of you guys did what I recommended and realized that, hey, this is actually up above the ground by, I think, by 13 centimeters. So if you add in that h is that plus 13 centimeters, then you got what the height was off the ground. That's fine. And I think that comes out to be something like 64 centimeters from the data from in class today. But the key idea here is that just that you can solve this all algebraically, that you have to take into account that speed at the highest point, and that really everything cancels out, and you can solve for that height in terms of r if you're looking for the minimum. There's no guarantee that that height is always 5/2 r, but the minimum that makes it work is 5/2 r, which is kind of a cool, nifty coincidence.